Hey everybody. Today we're talking about exponential growth and decay. Both of these are modeled by the equation y equals ae to the bx. When b is positive, this equation represents exponential growth, and when b is negative, it represents exponential decay. Exponential growth is pictured here on the left, and exponential decay is pictured here on the right. In each case, the rate of growth or decay is proportional to the population. Unconstrained population growth is often modeled with an exponential function like this. As in this example, the population of bacteria in a petri dish is 300 after 3 days and 400 after 4 days. Assuming exponential growth, how large will the population be after 5 days? After 10 days? We're going to start with the model P of t equals ae to the bt. Here I'm using p for population and t for time in that exponential model. And then I'm just going to take the values that I'm given and I'm going to plug them in. I get these two equations, 300 equals ae to the 3b and 400 equals ae to the 4b. Here we have two equations with two unknowns, a and b, so we ought to be able to solve these. The easiest way to proceed is just to divide one equation by the next. And we can get away with this because neither equation can ever equal 0. These are populations. When we divide, the a's immediately cancel. So I'm going to take the first equation and divide it by the second to get 300 over 400 equals e to the 3b over e to the 4b. And then using the law of exponents, that right-hand side becomes e to the 3b minus 4b. Simplifying a little bit, 3/4 equals e to the negative b, or e to the b equals 4/3. So b is the natural log of 4/3. Now I'm going to take that b and plug it back into my original model. P of t equals ae to the ln of 4/3 times t. Here we can apply another exponential rule to get a slightly simpler version of this formula. E to the ln of 4/3 is just 4/3. That's all to the t power using that exponential rule. That a number to a power to another power is the same as the number to the product of those two powers. So overall, I've got a times 4/3 to the t. Now I just need to find a. We can do that by plugging in either of the two data points that we're given. I'll use p equals 300 when t equals 3. Plugging that in and simplifying a little bit, I get that a is 8,100 over 64, which is about 126.56. So overall, we have this model. 126.56 times 4/3 to the t. We can check our work by plugging in t equals 3 and t equals 4. And when we do that, we get 300 and 400, at least up to the rounding error that we've made here with the a. Now we can get p of 5, the population at t equals 5, just by plugging in. We get 533. And we can get p of 10 just by plugging in, and we get 2247. In each case, I've rounded these results to the nearest integer, because I think our population shouldn't be a decimal in these cases. Radioactive decay is also often considered to follow an exponential model. In this case, we're going to have exponential decay. For example, a certain radioactive substance has a half-life of 87 years. How long does it take for 99% of the sample to decay? Notice here that we're not given any information about the size of the sample. So let's just pick a letter to represent this quantity. We're going to use Q for quantity, and so we'll use Q naught, Q with a subscript 0, to represent the quantity at time 0. It's an unknown coefficient here. Now we're going to do the same thing that we did in the previous example. We're going to plug in the information that we had, plug in the information we're given. At time t equals 7, the mass of the sample is supposed to be half as much as it was when we started. So it's 0.5 times Q naught. Plugging this in, 0.5 Q naught equals Q naught e to the 87b. The Q naughts cancel here. And then I can take the natural log of both sides to get rid of that exponential function on the right. Dividing by 87, I get that b is 187th times the natural log of 0.5, which is about negative 0.0079672. So here's our model. I've just taken out b in my original equation and replaced it with the number that I got. This is as good as we're going to do here since we're not given Q naught. We're not given sufficient information to find Q naught. However, this is good enough for us to find how long it takes for 99% of the sample to decay. We need to find t when q is equal to 0.01 q naught. The reason for that is that if 99% of the sample is gone, the amount that is left is 1%, so 0.01 times the original amount. Plugging in, I again get an equation where the q naughts cancel. I take the natural logs of both sides, simplify a tiny bit to get that t is about 578 years. Notice, by the way, that this result does not depend on the initial size of the sample. This is a hallmark of both exponential growth and decay.